Okay, so the next topic for the presentation is spacecraft sensors. Like for an object to either fly or remain in geostationary orbit around the Earth, they need to monitor the local and remote environments. Additional to that, many sensors on these aircrafts are used to determine environments that they are not directly involved in, including the atmospheric conditions back on the Earth. Like many application, this monitoring is undertaken by a vast area of sensors and sensor networks that work in unison to keep the space object in flight and keep it safe. Like the monitoring is quite important part for this spacecraft in determining whether there are any dangers to the spacecraft or the object, or like solar flares, or the possibility of another object hitting the object in space. So the first kind of sensor that is present in a spacecraft is the high gain antenna. The high gain antennas provide like a more precise way of targeting radio signals and are therefore very essential to long range wireless networks. They even amplify weak signals that are used in during a satellite communication. The high gain antennas transmit data to Earth on two frequency channels, like in the downlink. Like the one is at about 8.4 gigahertz, which is the X-band channel and contains like data about science and engineering, while the other channel, which is around 2.3 gigahertz, is in the S band and contains data, engineering data, but on health and state of spacecraft at low rate of 40 bits per second. The next kind of sensor that is present in a spacecraft is laser altimeter. The laser altimeter transmit laser pulses towards planetary surfaces with a typical pulse rate of like 10 to 30 hertz. The instrument measures round trip time, like the time of light pulse between emission and the return surface reflection, to determine the distance of spacecraft with respect to the surface. A laser altimeter operates in a very similar way to the radar technology, which uses radio frequency pulses instead of light pulses. Uh, uh, like an optical telescope is used to collect the received reflected laser pulse photons onto an photodiode. And the repeated measurements over consecutive orbits are used to understand the morphology of like the planetary surfaces and the construction, precise topography maps, like these things. The next type of sensor that is present in a spacecraft is the temperature sensor. It's like given the huge chances in temperature environments that sensors are subjected to in the space, they need to be like robust and not only measure very low natural environments, but they need to have capability of measuring any high temperature spikes resulting from solar rays or other high energy emittents. There are many different types of sensor that meet these requirements, which are employed in space and include laser communication terminals. There are also thermocouples, thermistor sensors, and thin film sensors, and RTD sensors. There are plans in the future actually of deploying temperature sensors that can measure temperatures at long distances and measure phenomena such as solar wind from a very long distance remote location. Um, so the next one is magnetic sensors. These magnetic sensors are not so well developed as compared to the other sensors that we have actually talked about, but their use is kind of growing. And like there are we can, like if we talk about Jupiter's magnetic field that has recently been created using a series of flux gate magnetometers on board of the Geno spacecraft. So the magnetic sensors that can be used for space applications are usually magnetic encoders, angular and position sensors. These magnetic sensors have a lot of promise for the positional and guidance sensors, as well as being used to map magnetic environments in space. So basically, these magnetic sensors are mostly for scientific investigations or the attitude sensing. The next one is the spectrometer. So, a spectrometer is basically a tool which is commonly used by astronomers, which splits the light collected by a telescope into its color. Uh, this method usually allows the astronomers to see the details in the light which are coming from the space, and these lights usually give a lot of information about the space objects just by studying the lights that is coming from the space. Like by using these spectrometers, we can find out the temperature of an object in space, learn from which direction it is traveling, or find out how fast it is going. Also, these spectrometers can help finding out its weight. Like we study the lights, they tell us even about the weights and even about what it is made up of. So these spectrometers help us learn all of this using the lights. The final sensors that I'm going to talk about is the initial measurement unit, which is already talked in detail by my fellow presenter. So I'll just give a brief about what is management measurement unit. So usually it is an electronic device which measures and reports a body's specific force. And along with that, it also measures angular rate and sometimes the orientation of the body, and using a combination of accelerometer, gyroscopes, and sometimes magnetometers. And these units provide like inertial altitude and velocity data to a spacecraft's guidance, also to its navigation and its control system. Like the IMU are very useful in the velocity data, providing the velocity data of the spacecraft. On a space shuttle, if we want to know, IMU data are used for converting the steering commands into control services, and engine gimbal or the reaction control system, that the thruster, also the thrust fire commands using the IMUs. uh, like usually one IMU is enough, but the shuttle has three for redundancy purpose. The shuttle IMUs are usually located to the forward of the flight deck control and display panels, so to get quite an accuracy with it. So that's all for the presentation. Thank you.